right, so welcome everybody to today's edition of the Quasiworld seminar. And our first speaker today is Tapio Rajala, and he will talk about BV and Sobolev extensions in metric spaces. So please, Tapio.
Thank you. So thanks for the invitation to speak here. So my talk will be, as usual, quite basic stuff. So I will just have a couple of definitions and results that are easy to show, and easy examples to show that the rest of the results cannot be true, which you might hope for. So what we will study is the connection first between PV functions and sets of finite perimeter, their extendability, and then see how it relates to extensions of W11 functions. And for this talk, the main paper one can read some more from is the recent preprint. Maybe this was last week or the week before, with Emanuele Caputo, who is a postdoc in Jyväskylä, and Jesse Koivu, who is a PhD student of mine. And if you happen to read this paper, please send me comments about all the mistakes you find, because for sure there should be some. So let's start with the definition, even though the audience probably is quite an expert on these things. So the easiest way to think about PV functions is to take the relaxation by Lipschitz functions. So you have a locally integrable function f, and we say that it has bound variation if we can approximate it locally by Lipschitz functions whose energy doesn't blow up, where we consider this energy to be the integral of the local Lipschitz constant of the function. Of course, there are equivalent definitions also in a very general metric measure space, but this is the easiest one, at least for me to think about. And let me, at this point, already point out that we are considering the setting to be just complete separable metric space here and a boundedly finite border measure. In particular, we are not making an assumption that the space would support a local Poincare inequality, which is probably the typical assumption to put here when you do analysis on metric spaces. And now for the PV functions, we can consider several norms which are not, which sort of the selection makes sometimes a difference when you are considering stuff in general metric measure spaces. So you could either take sort of the full norm, where you take the total variation, which is defined above, plus the L1 norm of the function. Or then you could just forget about this L1 part and consider the total variation part. So I will specify whenever we need both of them or just one of them. Or if I forgot to mention, then please ask for clarification. So this definition of approximating by Lipschitz function or approaching by Lipschitz functions, it was for open sets, and now you can extend this definition to all border functions by going from outside by open sets. And of course, if you're used to working with PV functions in metric spaces, probably one result that you would often use is sort of compactness. So if you have a sequence of say PV functions with the bound on the PV norm, then you would usually take a converging subsequence. But in our setting, this is not true. So if we are not assuming local Poincare inequality, then we in general don't have such compactness property. So we cannot extract locally converging subsequences from sequence of PV functions if we just look at the total variation part of the norm. And this sort of is the reason why in the general measure space setting, you sometimes have to take the full norm into consideration to have converging subsequences. So, okay, that was the definition of PV and this small warning. And what is a set of finite perimeter? It's just a Borel set whose characteristic function is a PV function. And now the first part of the talk is to connect the extendability of PV functions with the extendability of sets of finite perimeter. And this is intuitively quite an easy task to do. And what is the, well, maybe before going to what is the idea behind the interchanging the extendability of PV functions, sets of finite perimeter, one could say that even in the abstract metric measure space setting, the sets of finite perimeter and PV functions have many of the nice properties that you like for them to have. So there are, the perimeter is a local condition. It has lower semi-continuity because of the definition that was given by sequence of Lipschitz functions. So just taking a diagonal sequence, you have the lower semi-continuity. Then you have submodularity, and of course, by taking a complement of 1 minus the Lipschitz function for a sequence of Lipschitz functions, you get also the complementation property just from the definition. But again, the compactness was the one thing that was sort of missing for PV functions from the usual list of properties. And how to relate the sets of finite perimeter and PV functions is the quadrat formula, which holds in a general setting. So a function is PV if and only if the superlevel sets are, for almost every t, they are sets of finite perimeter and their perimeter integrates to something finite. And you can realize the PV norm by integrating the perimeters of the superlevel sets.
Tapio, a quick question. So
yes.
What are the assumptions on the underlying space here?
Here, do you need, so probably you need completeness, but you don't need really anything. So you don't need Poincaré, you don't need anything. So it should
I don't
follow.
think you need doubling either.
Yeah, you don't
completeness. I don't think you need completeness either.
Mm-hmm.
At least Michele did not assume.
Yes, of course, even in this, how it's written, I mean, omega is an open subset usually, so even here it's not.
Mm.
And probably you don't need separability or anything else either, so it's just from the definition. Yeah, so this is the basic tool to connect the sets of finite perimeter and PV. And so what are the operators we are considering and trying to connect? I put here this definition mainly to highlight that when we are speaking about extension operators or extension domains, especially in this case where P is 1 or we are talking about PV functions, we are not assuming linearity of the operator. Because this might be a strong assumption or it might not be. It's mostly an open question. So we are saying that the open set or a domain is a PV extension domain if we can extend every PV function defined on that open subset to a PV function in the whole space without increasing the norm by more than a constant multiple, this constant c, and well, it has to be an extension of the original function. So if you restrict it back to the set omega, it has to agree with the original function. And now you could consider this either with the full norm or just the total variation part, this question. Or then, of course, you can replace here this PV with any other function space and put a suitable norm or semi-norm for it. And you have the extensor property for that class. And now, if you're planning to zoom out from my talk, you can maybe think about this problem, which I've spent maybe too much time thinking about already, which is the linearity part. So the general question in this context is that if you just assume an extension operator as defined here, which is not necessarily linear, then you might wonder if there is a linear extension operator. There are some cases where this is known, or some contexts. One is when you have assumed that your space is a PI space, and instead of PV, you are considering W1P extensions. And here, the proof, at least which I know, is from Haivas and Koskela and Tuominen, which goes via the Haivas definition of Sobolev spaces. So you characterize the W1P extensions by those who have measure density and for which the Haivas Sobolev space is the same as the sort of local definition of Sobolev spaces. And then in this case, you can always give the extension operator if you are in a PI space with a sort of Whitney type operator, which by definition is then linear. But now you run into problem if you drop the PI assumption, then usually partitions of unity are harder to make work, especially you don't have the Poincare inequality to control the difference between average values, say on neighboring squares or balls or whatever. And then the other case where you have problems is when you are in this limiting case of PV or W11, where you cannot use continuity of maximal operator anymore, sort of to go to the Haivas definition. But yeah, still we know in a particular case of W11, the linearity, which is that if you are able to construct the extension operator, which is a Whitney type operator, then the construction gives you that, okay, your extension operator is linear. Or then if you happen to be in a case where you can make a trivial extension operator, which is usually just a zero extension operator. So this could be, for example, if you are a disk, say in R2 or ball, or a Lipschitz domain in a nice space. And so the questions for the open questions that are most interesting for me is there another way, even for the case of Sobolev extension domains when P is bigger than 1, but you are not assuming the space to be PI? Because I mean, there are many examples of extension domains in space where you are not assuming PI, of course. And sometimes the PI assumption is a bit strong to put. And then even in the Euclidean cases, when you go to dimension at least 3, where our constructions of extension operators do not work, then even in that case, it's not clear if you could give a say non-constructive argument for the existence of the linear extension operators. And well, maybe I give a few examples to keep in mind. So maybe they also highlight the difference between PI case and non-PI. So well, the first example would be maybe a disk in R2. So this is an PV extension domain because you can just extend by as the function itself if you consider the full norm. So this would be with the norm being the total variation plus then the L1 norm of the function. And this is well, this is a mostly calculation, but this holds for for Lipschitz domains. Actually, I guess you often write it as looking at the trace, and the norm of the traces would be bounded by the norm of the function inside. But then if you go to the homogeneous part, so if you just measure with the variation part, you cannot take zero extension anymore, because you could take, say, function which is equal to 1 on omega, or which omega is now this disk. But now what you are forced to do is if you just consider this total variation part, is you are forced to extend with a function which has zero variation. So this forces you to take as the extension of u just the constant function 1 on the whole space. And because of this, if you would consider 2 disks, you have disk 1 and disk 2. For this disconnected stuff, now you have 2 open subsets. This will be an extension domain with the full norm, or sorry, extension set with the full norm, but it would not be an extension set with just the total variation part, because if you take a function which is 0 here and 1 here, there's no way to extend it. And now, if you are in a setting of spaces which do not satisfy Poincare, you could of course just consider a domain like this, and then you would have these 2 disks here, say, inside, and you consider your measure to be just, say, the Lebesgue measure restricted to these 2 disks. Well, now omega is now a real domain, but again, you cannot extend, say, a function which is 1 here, 0 here, to a global. Well, is this the correct way to think about? Maybe this should go to the boundary or something, because here you can, of course, go to 0 there. So maybe one should put here plus the Lebesgue of the complement of omega, and I should change this drawing a bit. So let's put it like this. So the disks go all the way to boundary. So this would be the correct example. If 2 parts which are sort of analytically separated inside this omega, but they are not separated in the whole space. So that would be an example where the norm really matters. And then you cannot always take the 0 extension, because you could have something like the Koch snowflake, which I will not draw in large resolution. So let this be the Koch snowflake. So this would be still a PV extension domain. But of course, you cannot take the 0 extension. So if you have a constant function 1 here, the boundary would be the whole Koch snowflake, and that's not possible to have as a boundary of or as a, well, it doesn't have finite perimeter. That's the problem. So it cannot be the boundary of the super level set for almost every, or positive number of t. And yes, so these are maybe the examples to keep in mind. Any questions so far on this? So the first result that I'm aware of answering this question of connecting PV extension domains and extensions of sets of finite perimeter is from Budoka and Masia, where they considered only this total variation part, and well, had the result saying that PV extension property is the same as having the extension for sets of finite perimeter. And this is sort of clear from the coarea. So if there are 2 directions to go. So if you have your omega, so one direction is to go from PV extension to perimeter extension. So here it would mean that you take a set of finite perimeter on your domain, and now this set of finite perimeter, its characteristic function is a PV function. So you can plug it into your PV extension operator. What it will do is it will give you not a set of finite perimeter, but some function which has maybe this super level sets look like this. But now Quarea lets you select one of these super level sets for which the desired extension is, well, it's just a super level set of the global PV function. For the other direction, there is a minor problem, which is if you are going from perimeter extension to PV extension, which is that here's your domain omega. And so you start with the PV function. Well, you want to go from the PV function to sets of finite perimeter. So of course, the sets of finite perimeter you would consider are these sets UT, which are the super level sets of the PV function U. Oops. And now you can, each super level set you can extend to the whole space. You will get some set of finite perimeter whose perimeter in the space is controlled by the perimeter of UT in omega. But if you take just a random choice of extensions, then what you will have is here, if you take t to be a bit smaller, so then t prime here, then this red sub super level set, if t prime is t prime is smaller than t, then it will contain the previous super level set. But maybe your choice of extension would go somewhere inside the sort of previous extension. But what Burak and Masia noticed is that if you take the minimal extension, so minimal and same perimeter, then these will be ordered in the same way as the super level sets inside. Of course, in this drawing, these are not the minimal ones. They would go more or less along the boundary. So, for instance, if your omega is disk, then the minimal one will be just a zero extension always. But now, if these are nested in the same way for the extension as for the original super level set, then you can easily realize the extension of the function U as whatever these extensions of the super level sets realize as a graph of a function. So that was maybe the only thing that Burak and Masia had to solve in their proofs. But now if we go to metric measure spaces, so in PI spaces this works and it has been done already. But now if you go to a setting where you don't have the PI assumption, then the result is false. And it's false because you lack the compactness. And because of the lack of compactness, you have to put some assumption. So either you restrict the class of PV functions, so you put a bound on, for example, on the L infinity norm, then you can do the extension because this bound will give you the compactness, the desired compactness, or then you need to take also the L1 norm of the function into account. And then the L1 norm will give you the compactness. And an example to show that this is really needed is Well, I mean, all the examples feel like cheating, but maybe they are. Maybe they are. So if your omega is, say, this triangle here on the plane, and now you start to modify the reference measure so that you put here a geometric sequence of strips. This would be hard to draw, but say they are coming closer and closer to the tip here. And you put the weight, which, I mean, the simplest way is to put weight, which is 1 here, in this part. Then you would put in the next part, it would be 0 here. In reality, maybe you don't want to put 0 because it's a bit too cheating. Then it's 1 again here and so on. So if this is your weight, you would put and then you consider the Lebesgue measure times this weight as your reference measure m. Now you have disconnected these parts, this every second strip where the function makes leaves, and now you could put here a function which is growing as you are approaching this tip, so that you are still in L1. But now, if the function is constant on each strip inside this omega, and you are considering just the total variation, you are forced to extend as the same constant to the rest of the strip. And well, here the Euclidean volume is going like r squared if this is r, this distance to the end, and for this part of the space, the volume is going like r. So you can easily construct an example where here, once you have extended as the same constants on these strips, you will not be locally integrable on these lines here. Well, maybe this is not the most important example, but it still shows that without the PI assumption, you have to be a bit careful making the proofs. So okay, that was the connection between PV and sets of finite perimeter, and it was basically just Quadria form and nothing else. So now let's go to W11. So how do we connect the perimeter extension and PV extensions to Sobolev extensions? And in the Euclidean case, where this boils down to philosophy quite easily, is the fact that the Sobolev functions are exactly those PV functions for which the total variation as a measure is absolutely continuous with respect to the Lebesgue measure. I mean, this is not true in the metric space setting, but in Euclidean setting it is. So you can exploit this to give the following characterization, which is that you are a W11 extension domain if and only if you are a PV extension domain with the additional requirement that when you're extending the PV function, the total variation of the extension at the boundary should be 0. And when you turn this into the perimeter world, it means that you can extend any set of finite perimeter to the whole space so that the mesotheoretic boundary does not intersect the topological boundary of the domain in a non-zero mass with respect to the codance of one measure. So here there's sort of two things to solve when you are proving this. One is that you are jumping between PV and W11. So what you want to do is you want to say, if you would assume that you are W11 extension, and you want to show that this implies that you are a strong PV extension. So what you do is, well, here you are forced to take a BV function says you are proving the extension for BV. So take your BV function. But now you are given a W11 extension operator, so you cannot feed your BV functions to your operator. So you have to go from this to another function, say u tilde, which is in W11 instead, which we would like to extend. And you want to do it so that you're not changing what happens at the boundary. Well, luckily there's a quite standard way to do this in the Euclidean space, which is that you make a Whitney decomposition here, and you take a partition of unity with respect to that, and then plug in the BV function there. You will get a smooth function which doesn't increase the BV norm by more than a constant multiple because of Poincare inequality. And so this is sort of the first thing you have to solve, that how do you find the correct functions to fit to the extension operators. And the other problem which you have to solve here is the one that Buraga and Masia solved by taking the minimizers. Was that if you have this two superlevel sets of your BV function, and you would like to extend them to the whole space. So Buraga and Masia, they took the minimizer of the extension, which usually goes along the boundary. So we cannot take this because we want to avoid the boundary, because we are making these strong extension operators. So we are just given some extension here. And we don't really have control on where it goes. And then we have the other extension, and these no longer need to be sort of inside each other. And even worse, they know the selection of these extensions doesn't need to be measurable. So you cannot say just integrate up the super level sets to get the correct object. But well, it's just, I would say this is just a technicality that you have to find some way to go around. And the way we took with Mikael was that we take just some of these super level sets and their extensions, and we build a simple function from, say, finitely many of these. So that will be measurable, of course. So essentially you just integrate or sum up the characteristic functions of these sets times, say, the difference between T and T prime. And then you go to the limit and show that the limiting function, you can select this super level set so that the limiting function still has the bound for the extension. So these were the two problems one had to solve in this result. So now when you go to metric space, well, there are several new problems that you face with. One is that this step of going from W11 or from, say, BV functions to W11 does not work because you cannot make a Whitney decomposition and use the Poincare inequality to control the smoothened object. Well, this trick still works, so this is a general trick of going via simple functions. This is maybe not so surprising. It doesn't change. But there's also the problem of having several definitions of Sobolev functions. In particular, in this result, we used the fact that the W11 functions are those BV functions that are absolutely continuous with or whose total variation is absolutely continuous with respect to the reference measure. Well, this is one definition of Sobolev you could give. in a metric space setting. The problem is that not many people would use this definition, maybe, because it's not nicely connected to the usual definitions where you have curve-wise conditions. So the definition from Nages or the definition of using test plans, which I put here as the second definition. So usually you want your local definitions be of this type, that you reduce the testing of the Sobolev property to testing the Sobolev only along curves. And now there are several different ways to study what do you mean by almost every curve here. If you take the approach of Ambrosia, Gili, Savare, and others, then you would start with a test plan, maybe an infinity test plan. If you take the one of Nages, you would then go to a modulus world and have the same condition. But in any case, these definitions that are curve-wise, they are really different from the definition of where you just assume the total variation to be absolutely continuous with respect to the reference measure. So it's quite easy to see that you have this inclusion of the definitions. Say, if you start with the test plan, it's strictly included in the sort of weak W11 space if you just allow for the correct structure. So maybe the easiest example is to take again a disk because it's easy to draw, and then as a reference measure, you take the Lebesgue measure plus the Hausdorff one-dimensional measure restricted to the boundary of the disk. So S1. So here, for instance, now if you take as your function just the indicator function of the disk. So it's a PV function, of course, with respect to the Lebesgue measure. And because of that, it's also a PV function with respect to this measure here, this M. It's also now in this space because we added the measure of the boundary. So the total variation lives on the surface of the disk, and it's absolutely continuous with respect to the one-dimensional Hausdorff measure. So this means that the total variation is now absolutely continuous with respect to a reference measure, and therefore we are a Sobolev function. But of course, this is not the kind of function you would like to have for your, say, test plans or models. So you take curves that are going from inside to outside or vice versa, and you're making a jump from 1 to 0. So there's no way to put here L1 function that would serve as an upper gradient. So these are different objects. And so because of this, we have now more conditions to study. So we have the condition for Sobolev where you are assuming the absolute continuity of the total variation, and then these more traditional definitions. I've lumped them here as just one class. And now you can ask, if you are in a space where you don't have Poincare inequality, are these equivalent, these extendabilities of different notions? And the answer is that no, in general they are not. So the first two are equivalent, the extendability of sets of finite perimeter in a strong way, and extendability of PV functions. This is because the quadria still holds, essentially. Yes. I mean, the proof from the Euclidean case doesn't change much. But now when you jump to Sobolev, the problem is that the boundary of your domain could have positive measure, and this spoils everything. And it also spoils in the second implication everything, that you cannot go back if your domain if the boundary has positive measure. I will soon give a couple of examples so that the inverse implications are false in general. But now if you put the additional assumption that the boundary has measure 0, then actually these all definitions are equivalent, or all the extensor properties are equivalent. Okay. Yes, but and again the procedures are quite the same as in the Euclidean case. So you have to go from your function, say, which is just in BV, you have to go to a Sobolev function with some smoothing operator that doesn't change the value at the boundary. This time you cannot use the Witty type operator to make the smoothing, but still you can make the smoothing without the Poincare inequality. Your function will be just Lipschitz, but that's local Lipschitz, but that's fine. And the same kind of thing you would have to do in other steps as well. So let's see what are the examples of showing that the implication from the usual Sobolev extendability to this weak type Sobolev extendability does not, well, sorry, the converse doesn't hold. So if you assume that your domain is extension domain for W11, so weak definition where you're taking just the absolute continuity, so it doesn't give you the extendability for W11, and the example is always the same as you saw in any Sobolev space courses. So maybe disk is not enough, so you take the slit disk. So you have your omega is the disk minus a slit, if this is the slit. Well, this is a BV extension domain. Of course, if you just take the Lebesgue measure, it's not a W11 weak extension domain. So you have to modify also the reference measure. So you take the Lebesgue measure plus then the one-dimensional Hausdorff measure on the slit. So it's quite the same as the previous example, but now you put the Hausdorff measure here. And now if you take a W11 function inside omega, doesn't really matter which definition you take, because now you're in a Euclidean setting inside the domain. You have no problem in extending, say, a function as a BV extension. So even if you are 0 below the slit and 1 above, you are allowed to make the jump here. And this jump is, of course, fine with respect to this definition of weak Sobolev, because now the total variation again leaves, for this jump part leaves on the slit, but we added this measure, making it absolutely continuous again. The only thing you have to worry about maybe slightly is that we are not making necessarily a 0 extension here. Well, actually, now that I think about, maybe it was that you can make a 0 extension of the function for the slit. So, yeah. But again, the same reason as before, this is not the W11 extension, because there are these lines passing through the slit, and no matter what extension you take, you will have still a jump from 0 to 1 on positively embedded lines, and you are dead. So this is the example for the first failure. For the second one, well, I will show you just the cheating example because it's the simplest one. So W11 means that you can extend as a W11 function in a usual way, with the sort of more classical measure space definitions. And strong BV meant that when you extend, the total variation has to avoid the topological boundary. So now we can just, if you make a cheating example, we can make something like this as your domain. Maybe this is an old telephone for those who still use those. And you just play around with the reference measure. So you put just measure here. So you put your measure to be one-dimensional Hausdorff measure on this line L. So now you force the topological boundary of omega to be in a large part here. And if you now make a function which is just called red, which is 1 here, 0 here, then you have to go from 0 to 1. The relevant part of the space only where this measure lives. So it has to increase on this line, but this line is now on the topological boundary of omega. So this will not be a strong PV extension of the function, since the increase is happening on this line set. Now you could make a more complicated example where you either add some more measure here, so that say this part of the measure is analytically disconnected from the rest, or then you could hook up with a more exciting example, maybe having similar property, which is, I mean, the example is roughly that you start to take away balls smaller and smaller. So this would be just an open set, not the domain. So this side would be the domain, but now you put the weight on the plane so that you can extend each of these disks separately to a small neighborhood. So what you are forcing is that you would have a function which is 0 here, 1 here. Maybe almost every line does not see this cloud of small points, balls, but still you are forced to go from 0 to 1 here. You are avoiding the balls, so it means that you must be on the topological boundary if these balls are dense in the space between. But now, I mean, it's a bit more complicated because you have to find the whole correct densities here. But yeah, so still, I mean, either there's sort of a trivial example to the converse implications, or then you can prove them. That was the outcome. So there was the one technical part, which was the smoothing, which in the Euclidean or PI space case you can do by just a Whitney decomposition. So you take a Whitney decomposition, you take a partition of unity subordinate to this, so VI subordinate to this partition of unity, and then you define your new function, which is this SPA here. Right? Of u, it would be just the average value of u inside these cubes times the partition of unity. So a typical Whitney type stuff. And you just have to check that for this kind of operator, you are not changing the boundary values. And the good thing about this operator is that this is a linear way to do it. So if you can, so what this essentially means is that if you can find linear extensions for PV in a strong way, then you can find also linear extensions for W11 in the setting of PI spaces. Well, this doesn't work in the metric measure spaces where you don't have PI, because there's no way to control the gradient of such a guy. But you can still do in smoothing in the non-PI space case. So what you do is use the definition of PV, and then something which you probably have seen on many courses is you make an annular decomposition of the domain. So you start to empty it, and you have this annular parts closer and closer to the boundary. And now you, from the sequence of converging local ellipsis functions, you just take elements further enough in the sequence. And you have to just take care that all these properties that you want are satisfied, but this is doable. I guess I'm at 50 minutes now, but maybe I can just shortly say where these kinds of stuff can be used. I mean, where is it useful to connect the PV extendability with the or W11 extendability by extendability of PV sets. One thing is that in the Euclidean case, you can characterize, well, you can give conditions that are sort of more geometric, GMT type. So a W11 extension domain has to have the property that whatever is left out from the domain, if you take all the closures of the holes away, sort of, so there might be some Cantor part, but this part has to be purely n-1 unrectifiable in the sense that I wrote here. And now if you go to the planar case, this becomes an if and only if condition. So it will, the extension domains are exactly those for which the remaining part will be those PV extension domains for which the remaining part is purely one unrectifiable. And how this is done is by the decomposition of sets of finite perimeter. So in the planar case, well, in a metric measure space case, if you have PI, you can still make decompositions of sets of finite perimeter. But the point is that if you go to the plane, your decomposition reduces the study of sets of finite perimeter to just Jordan loops. So yeah, you reduce from W11 functions, you go to, say, strong PV by co-area gives you that you are studying sets of finite perimeter, and then you can reduce the sets of finite perimeter to just Jordan loops. And now you're back to curve conditions. So you, in particular, have you can reprove by this method the characterization of W11 extension domains. But yeah, this was really fast for the applicants, but I will stop here.
Okay, thank you, Tapio. So let's thank the speaker. And let me start the discussion here. Are there comments or questions? Also, let me ask a question. Can you say something about future directions here? So where do we go from this?
From this, well, there are a couple of directions. One is maybe to the linearity, because now maybe you can sort of extend the sets of finite perimeter still by ordering the sets for the extension in the right way, or taking minimizers of other stuff than what the Urako and Masia did. One thing which we are considering now is to look at when do you actually have these extension sets. Because in the PI space case, you can approximate domains by extension domains. But now in the non-PI space case, it's not so clear.
So can you go back to one of your last slides? I mean, this result, yeah, exactly. This one, yes. So can you maybe say more about, we can quite easily reproof. So what do you mean by this?
Well, I mean, it's reproof because this is something we did with Pekka and Yi. So what we did with Pekka and Yi was we constructed the extension operator by you have your domain, omega, you take a conformal map from the disk to it, and now you have to decide how do you make extension. So you make a partition of unity, but now with triangles. So you take sort of these hyperbolic triangles and assign. So make a reflection by assigning, say, a value from here to this line and fill in the hyperbolic triangle or quasi-hyperbolic triangle in the exterior. But this is a bit difficult way. So it's easy compared to this. So that's the first.
This was the original construction. But
so this was the original construction. The good thing was that this gave a linear operator, which is now, I mean, it's the only non-trivial case where you have a linear extension operator in W11 that I'm aware of.
And you really mean simply connected, not Jordan here?
Yes, it's simply connected. So we do it via Jordan. So
so you do
limit procedure, but do we? But you could do it also directly. But there's sort of problem that these sets are collapsing, these hyperbolic triangles. So they are not as nice as in this picture. But now, so what we are reproving is just having this condition as if and only if condition for being W11 extension domain.
But not necessarily by a linear operator.
Yeah, we are not taking the linear extension operator. And how do we do this is, well, I would have a picture of it in another slide. But so you reduce everything to extending just Jordan curves. So you have your domain, maybe it has some, maybe it has some holes even, if you want. And then you have some Jordan loop going. So this would be maybe a PV extension of the original object. So in this picture, it's not the PV extension. But now what you have to do is you have to kick it away from the boundary at each component. And I guess this went back to maybe results of Rajala and others that you can really do such things.
Okay.
But it was, yeah, reducing everything to Jordan loops. And then of course this you have a curve here, so that's already almost like a loop. You just have to complete it.
Okay, yeah, thank you. Our time here is running out, so maybe it's a good place here to stop this discussion. So let's thank Tapio again.
Thanks.
Yeah, and let's get ready for our next speaker here. Let me actually stop the recording at this point.